So last class, we kind of talked about the Compact Logix PLC, and the one that we have in the classroom has this analog IO card, and I believe I wrote this number down correctly here. It's like IF4, which means 4 inputs, right? The I there, and the 4 indicate 4 inputs. I'm not sure if the F means fast or not. I'm not quite sure what the F and the X actually mean. If somebody knows, be glad for you to let me know. But and O is outputs. And again, I'm thinking the F is fast and the 2 outputs. So it has 4 inputs, 4 analog inputs, and 2 analog outputs. And this card has so these 4 inputs and these 2 outputs, each one of these inputs and outputs can either be a current input, if it's an input, it can be a current input, or it could be a voltage input. And if it's an output, it can be a voltage output or a current output. And so, like, I know, like, some of the cards, especially the older style, like the Control Logix, that we will use the Control Logix for a couple of labs, but their output card is either a current card or a voltage card, but not both. Okay, so so it kind of depends. I think some of what it depends on is the age of the PLC. The older PLCs, I know they had, when you bought the card, you either bought a current output card or a voltage output card, but not both. But this particular module, which is the 1769, meaning you can plug it into a Compact Logix card, it actually, the output can be either a voltage output or a current output, and the inputs can be voltage inputs or current inputs. But remember, just like when you're wiring up a digital multimeter, if you're going to wire up a digital multimeter as a voltage, you wire that in parallel, and it has a high input impedance. If you're going to try to measure current with your DMM, then you have to physically, there's actual physical different connections that you have to connect to wire it up and measure current, as opposed to if you're wiring voltage. So that's exact same thing with a PLC. If you want to use a PLC analog card to read in a voltage, right, then you would, it's going to have a very high input impedance. But if you're going to wire it up to measure current, then it's going to have a much lower input impedance, and you have to physically wire it differently. So they have different wirings depending on how you're going to wire it up. Okay. So just kind of remind you, these were from the first slides here. We talked about the different types of analog signals. And so we have voltage signals, and the voltage signals could be either 0 to 10 volts or possibly 0 to 5 volts or minus 10 to plus 10 volts. Okay, and you could also have very small analog signals, but if you're going to have something like that from a sensor, from something like a thermocouple or load cell, you're going to have to run it through one of those converter devices to get it up to something that is more readable by the PLC's analog card, or you have to buy a specifically dedicated card to read such a small signal. Okay, and the current signals, 0 to 20 milliamps is a valid input current signal. But normally the sensors deal with the 4 to 20. And again, the reason for that is a non-zero current tells you that, hey, it's working. So so if your sensor is reading, like, just say you're trying to measure how much water is in a tank, and your sensor says there's no water in the tank, it's actually going to output a 4 milliamp signal instead of 0 milliamps. And that, the purpose for that is basically it tells you that if you're getting a 4 milliamp signal, you know the tank is empty, but the sensor is actually working. Where if you're getting 0 milliamps, it may be that the sensor's broke or the wire got cut between you, the PLC and the sensor or things like that. So that's why we like a non-zero starting current signal there. So if you actually have no current, then you know it's a wiring issue or broken sensor or something, as opposed to the tank just being empty. Okay. And so currently what I've got set up here is I've got output channel 0 is going to output a signal, which is going to be a current signal. And I might flip it back and forth. I think right now I have it set to a 4 to 20 milliamp signal. And I've got it wired in to my 3 of my inputs. So I've got it wired into channel 0, channel 1, and channel 2. So remember that the PLCs and most computer stuff, they like counting from 0 because they're counting in binary and just like selecting which device. And so that's why they kind of start counting as 0. So there's 4 channels on this card, but the numbers of the channels are 0, 1, 2, and 3. All right, so anyhow, so I've got this wired up using a daisy chain. All right, so I've got my 4 to 20 milliamp signal is coming out, and I'm actually feeding it into the 3 inputs. And so I've got it daisy chained in here like we talked about during the first week. And so I actually have this running right now. So if I come over to my RS Logix 5000, we can see here is my main routine, which is pretty much what I had in the previous lecture. And so I've got a couple of timers here, timer 1 and timer 2, which are just like doing a tick-tock back and forth so that it keeps the timers going. All right, and so they're going through and they're counting, and I've got a counter, and you can see here this counter is counting up 0, 1, 2, 3, 4, and 5. And when it hits 5, the counter is done. And when the counter is done, it resets. Okay, so you see there, you never see it 5. Let's look at this counter for a minute. 1, and it's running for about 3 seconds. So it gives me a little bit of time to talk while it's running here. So, right, but it's counting up 1, 2, 3, 4, 4, and you see it. You didn't see 5 appear. Now the reason you didn't see 5 appear is because remember that ladder logic works where it's going down the ladder. All right, and this is something that you have to be careful when you're programming ladder logic, that you keep in mind that the rung up top, like right now, rung number 4, when it hits 5, okay, it does hit 5. But once it hits 5, then the counter done bit is done. So if we come all the way down here to rung 9, when the counter is done, it resets. So what happens here is in the exact same scan, that counter is hitting 5 and then being reset to 0 in a single scan. And so in a scan, I don't know exactly how long a scan lasts, but remember, it really depends on the speed of your PLC. So chances are a scan is happening once every millisecond or something. So it's happening, boom, so quick that you're never actually ever going to see that counter value actually 5, because it's being reset within, it's actually being reset within 5 rungs. And so if it's running the entire scan in 1 millisecond, it's running through these rungs in microseconds. Okay, so it's actually executing this code so fast that you're just never going to see that happen. All right, but what I'm doing here then down below the counter, so we see it counting 1, 2, 3, 4, 5, and this is something you may have never done before, but remember that all numbers inside of a computer, whether it's a PLC or your cell phone or what, all the numbers are stored as binary numbers. And so what I'm doing here is we've got the accumulator, right? This is the accumulator value of the counter, right? And the counter is going 1, 2, 3, 4. And what I'm doing here is I'm actually using a move statement to move that out to my relay modules. Now, you can't actually see the PLC. It's actually down in my basement at the moment. So, you can't see those relay modules working. But what you can do is watch this count. So if you look at this value piece over here, you see it's going 4. That is 4. 1, 0, 0 is 4. 1, 0, 0, 1 is 5. Okay. So it actually did hit 5 there. So it moves it out. Okay, it's doing that move only when the timer is done. Okay, and so it actually holds that 5 out. It actually sends that 5 out to the relay, and it holds it till the timer recounts again. All right, so you can actually see that 1, 0, 0, 1. That's 5 in binary. All right, and then you can see that's 2 in binary right now. 1, 0. 1, 1 is 3 in binary. Right. 1, 0, 0 is 4 in binary, and then 1, 0, 1 is 5 in binary. So you can see it like outputting those values right there. And what I'm doing is when the least significant bit is a 1, okay, so when the least significant bit is a 1 right here, I'm moving 2500 to my output. Okay, so I'm moving 2500 to my output. And when output is when the second bit, okay, so when this is actually number 2 right now, you see that this is active down here. I'm moving 5,000 out to my output. And when I hit 4, so when my output or my third bit, so when this third bit right here hits a 1, right there at 4, right? That's 4 in binary. That third bit is when that is a 1. When the third bit is a 1, I'm either at 4 or 5. I'm outputting 10,000 right here. Okay, so I'm going to move 10,000 out. So now, if you remember from the previous lecture, I actually have the analog output set up to be a percentage range. And so that percentage range, and this was actually the file I had open the other day, but that percentage range, if it's 0, it's outputting 10,000. All right, because this was like 100. Technically, it was like 100.00%. Okay, and so 10,000 is 100.00%. So it's an integer value, so you're not allowed decimal points. So what they did is they multiplied it times an extra 100 to allow you to be a little more precise. And so what I've got is I've got this card running. My output is running 0, right, which is 0%. or 2500, right, which technically would be like 25.00%, but that's 25, so it's outputting 2500, or it's outputting 5000, which is 50%, or it's outputting 10,000, which is 100%. But now if it's actually a current, okay, so if it's actually putting out a current, all right, so here it's actually outputting the current. The current is going to be 4 milliamperes, which technically is going to be 4,000 microamps. Or it's outputting at 25%, okay, at 25%, it's actually going to be outputting 8 milliamperes, because your range, you have like 25%, well, you know, you have the range there is 4, 8. I mean, you could do something, if I wanted to, I could do something like you know, 4.125 milliamps or something, okay, or some fraction. I could do 4.003 milliamperes or something if I wanted. I'm just not outputting that right now, okay, but I could output virtually any value in there. But right now what I'm outputting, 25% would be 8 milliamperes, or 8,000 microamperes. Okay, and 50% is 12 milliamperes, okay, or 12,000 microamperes. And of course, 100% is my 20 milliamperes, right, or 20,000 microamperes, okay? And so I wanted to illustrate this, because when we come over here and when we look at the setup, okay, so I'm outputting a percentage, but on my input, I'm also inputting the percentage right now. But I'm going to change this because I want to try to illustrate this a little bit better than I did the other day. So when we look at these tags, okay, I have these input tags and the output tag. So you see the output tag's actually on top. And so when the output tag is outputting 5,000, you see that the input is, for some reason, I'm not 100% sure why, channel 0, channel 0 is a little bit less. So you see like 5,000, it's at 4,600. I'm not sure why that is. And then the channel 1 is at 5,000, and channel 2 is at 5,200. Okay, so I'm a little, because they all should be exactly the same, but there's a little bit of difference in there. I'm not 100% sure why that difference is there. It's kind of interesting to see that run, because I'm running this I'm running this signal through there for all of them. So you see, like when it goes to 0, so right now I'm outputting 0, and we're actually seeing a slight negative value, okay? And then I'm going to 2,500, and you see that they're a little bit below that. And then 5,000, okay? And I'm not actually seeing it sit at 10,000 here, okay? So it's not actually, the problem is it's being reset before the 10,000 is actually output, okay? But so right now, what I'm actually outputting is either 0, 2,500, which is 25%, which should be 4 milliamps, or and that. So what I want to do to illustrate this now is I'm going to come over here to my configuration of my analog card, and I'm going to set the first one, I'm going to set to what we call the raw or proportional. And then the next value I'm going to set to the engineering units. And then the last one I'm going to keep a percentage. Okay. And so I've done this now. So remember, with, you know, if I'm outputting 5,000 like I am at the moment, that is 50%. Okay, so 50% is 12,000 milliamps. So channel, so let's see. So channel 0 is raw, which is minus 30,000 or 32,000 up to plus 32,000. Okay, and I guess the other thing is, let's look at the other setting. I didn't double check that. I think it's actually reading 4 to 20 right now. I'm going to actually change it to 0 to 20. So I'm going to read in all the way from 0 to 20. Okay, so I'm reading in 0 to 20 because when you look at an analog to digital card, even though the sensors, most sensors that you're going to buy that output current are going to output a current signal from 4 to 20. However, technically, the analog to digital card is actually always going to read from 0 to 20 milliamps. Okay, so your input card is actually always reading that. And so when we flip over here and just look at these inputs now, right, you can see there that right now I'm at 0, but it's reading 4 milliamps, 4,000. It's 3.88. Okay, 3.88 is basically, you know, it's close to 4 milliamps, right? So this is in microamps, okay, because they scale it. And by the way, when I click on this, it doesn't update, so that's why it seemed like it wasn't changing. So now we're at 5,000. You see 5,000 is 12,000 microamps. And that's what it's reading. When you go to engineering units, this was engineering units. Notice they have these descriptions for the tags, which is kind of nice. You can kind of label them, and so I can kind of state what they are. And this one was percentage. Okay, so so this one is percentage. So notice now at 5,000, okay, the reason the percentage is different than this percentage is because this percentage up here is outputting 4 to 20 milliamps, but these guys are reading in at 0 to 20. Okay, before I had them reading in at 4 to 20, so they were a match. But now I've got them reading in, so it's reading in 0, and that's why the percentage piece is higher, because it's reading, you know, 0 doesn't actually start till 4%. And so it's, the percentages are different. So, but what I really wanted to illustrate was these engineering units, all right, and the raw. So notice the raw here at, we're outputting 4 milliamps when it's 0. Okay, so when it's 0, we're outputting 4 milliamps. And so raw is like minus 20,000. Okay. And then when it's a 5,000, okay, raw is, you know, slightly a 0. Okay, so let me change it because I'm not getting the 10,000 in here. So I'm going to just modify this code just a little bit to, okay, so I'm going to change my counter preset value up to 6 maybe. Okay, 1, or did I not? Yeah, so that should be outputting 10,000 over here. Let's see, give it a second too here. Should hit 10,000. Okay, it's not going to 10,000. Oh, okay, I see. I've got the wrong bit there. Hold on, I've got accumulator 3. It should be 2. That's what's going on. Okay, so this should be a 2 also. All right, so what I'm doing here is I'm selecting these bits as they go across. All right, so let me download it again. All right, so now if we look at these tags, all right, so you see it's a 2,500, it's a 5,000, and now it's a 10,000. So 10,000 is actually, it's outputting, and the raw value was outputting at 10,000, the raw value is outputting. Man, that's running really fast. So I'm going to change my tag here. I'm going to slow it down a little bit. So I actually have this value, so I can kind of slow down my counters a little bit here. So they're changing the accumulator. So okay, so you see there at in raw, when it hits 10,000, the raw value is at about plus 20,000. And when it hits, okay, 5,000, it's out, the raw value is 3,000. The current is 12,000 because the 12,000 is means that we're outputting 12,000 microamps. That's what that's saying. All right, 12,000 microamps is equivalent to 12 milliamps. And when we're at 10,000, we're outputting 20,000 microamps. So that's why you're seeing 20,000 here when we hit 10,000 here in a second. There's 10,000. So it's outputting, it's not quite getting, the current's actually not quite getting to 20 milliamps. I think I got this card overloaded, okay, because I am driving this card. I didn't read the specs on the card, I just wired it up. So I've wired this output card, that this output card is outputting 3 separate inputs, okay? And so I might have the card a little overloaded because it seems like it can't quite get to the 20,000 milliamps that it should be getting. And so I think I might be overloading the card. Maybe I shouldn't have hooked up all 3 of them. All right, so but you see there 12,000, okay, it's outputting 12,000 microamps when I'm in engineering units. All right, so let's take a look at scaling though. So the problem with this is the fact that, remember that coming into our PLC, these are our inputs of our PLC. So coming into our PLC, we're actually inputting a current. And so that current is somewhere between 4 to 20 milliamperes. And that's what we're feeding in. So what I normally do with my configuration for this PLC is I actually usually I use engineering units. Okay, I don't really like messing with the raw. I like using the engineering units because sometimes the percentage is nice to work with. But the you know, so now you can see, right, when we're outputting, the card is outputting 0%. That means it's out, that means like the tank is empty. And if the tank is empty, then we, let's see, so if the tank is empty, where the sensor is outputting 4 milliamperes, okay? Which is 4,000 microamperes. So that's like right now it's showing us 4,000 microamperes. When it's a quarter of the way full, we're outputting about 8,000 microamperes. And when it's half full, so like right now it's half full, we're outputting 12 milliamperes. And then here, again, I think it just can't quite handle 20 milliamps to 3 of these, I think is what's happening. So it's supposed to be outputting, you know, when this outputs 10,000, it's supposed to be 20 milliamperes, but it just can't quite make it, is what's happening here. I'm overloaded the card. So I hope I got a good warranty on there. So I should, so that's why it's not quite making it up there. So, but what I want to do then is talk about scaling. So if we look at scaling, let me get the scaling slides over here. Okay, so the problem is that your sensors, remember that a sensor is converting some process variable. We talked about that like the first week. We have a process variable, could be a temperature. It could be how many gallons of water are in a tank. It could be a pressure, how many PSI. It could be a weight. Like load cells measure weight. Okay, so this so we want to measure something. Okay, so we're going to use a sensor or go out and buy a sensor so we can measure something. We can measure how much is in a tank, what the pressure is, what the temperature is, you know, how fast something is moving, how many revolutions per minute something's spinning around. We want to measure something. So we're going to measure that. So we buy this sensor and that's going to measure this, but to measure it, it converts it into this signal. And so that signal, in this case, is a current signal. And so we need to scale it back into whatever it is. Okay, so we want to scale it back into whatever it is. So like, for instance, if we have a load cell can measure a weight. And so, and we're going to be working with load cells for at least a couple of the labs in the class. And so the load cells that we have in the classroom, what they do is they measure, they can handle 50 pounds. So the load cell, if you don't have anything on the load cell, it's going to output 0 volts. If you have the load cell loaded as much as it can handle without damaging it, that would be 50 pounds. And so what happens with this load cell though is, you know, so ideally, if the load cell is a perfect load cell and you have nothing on it, it's going to output 0 pounds. If the thing is loaded down, it's going to output 45 millivolts. Not 50 pounds, right? It's going to output a voltage. Okay. What we're going to do then is we're going to convert that voltage into a 4 to 20 milliamp signal and feed it into our PLC. Okay, but what we really want to know, you know, honestly, we don't care whether there's 13.7 milliamps coming out of this converter. What we care about is how much weight the load cell actually has on it. So what we have to do is we've got to take this 4 to 20 milliamp signal or whatever it is, and convert that back into pounds so that we know how many pounds is that. So what we got to do is review a little bit of very basic geometry, all right, and a little bit of algebra here. So if you wanted to draw a straight line, okay, so think about a straight line. Fortunately, a lot of our sensors are linear, which means that they're going to have a nice straight behavior. So the voltage out or the current that they put out is going to be linearly related to what they're actually measuring for us and sensing for us. And so the slope of a line is the M piece here. So this is the equation for a line in algebra. So this is why we make you take the algebra class. So hopefully in your algebra class, you talked about the equation of a line. So the equation of a line, we have, this is what they call the slope-intercept form. So you have the slope, which is M. Okay, so M times your X value plus your intercept, so B is the intercept, okay, will scale this and give you your value. Okay, so the slope, we determine the slope using 2 points. Okay, this is a negative slope, but to find the slope, we have to pick 2 points on this line. All right, and it's a ideally, it's a perfectly straight line, so you can pick any 2 points anywhere along there. And so you have point x1, y1, and then you have point x2, y2. And so the slope M is defined as being the y2 value minus the y1 value divided by the x2 value divided by the x1 value. All right, so those are our 2 points along this line, and that will give us the slope of the line. And now once we have the slope, we can calculate B, okay, using these same 2 points, y2 and y1. Actually, we only need one of those points to calculate B. So if you look on the next thing, the B is where it crosses on the y-axis. And so we can either say that B is equal to y2 minus M times x2, or we can use the y1 point minus M times the x1 point. All right, now typically, one of these, if we use the y1 and x1, a lot of times either y1 will be 0 or x1 will be 0. Not all the time, but some of the time, one of them at least will be 0. And so what we can do there is we can use either equation. But if you pick the equation where one of your values is 0, it just makes life a little bit quicker and faster. Okay. All right, but what we need to do is we need to find this slope and find this intercept for our particular sensor. So here is an example. All right, so in this example, we have the load cell has a maximum range of 75,000 pounds. So this is a really big load cell. The ones in the classroom, the load cells we have in the classroom can only do, what would I say, 50 pounds, right? But they make these same types of load cells so that you can actually drive trucks on them, all right, and weigh a truck. Right. So this is a load cell here that in this example, it can handle 75,000 pounds. Now, at these 75,000 pounds, the load cell is going to output 45 millivolts. Okay. And if nothing is on the scale, it's going to output 0 millivolts. And so we can then find the slope. So we have 0 pounds and 0 millivolts, and we have 75,000 pounds and 45 millivolts. And so given that, we can then find these are our 2 points. Okay, this is like y1 and x1, and this is y2 and x2. So we have our points that we can find the slope of the card. And so now these are given in millivolts. Well, like I say, what we're going to do is we're going to wire these up to a 4 to 20 milliamp converter on there, and it's going to output these milliamps. So just for today, I think I'll start with a kind of a simpler example. What we're going to do is we're going to assume. I'm going to duplicate this slide here. I don't want to lose this slide, but I'll make a copy of this slide. All right, and so let's just assume, let's do a simpler example here. Load cell is, let's just start out here pretty easy. Let's say that the load cell is going to output 0 milliamps at 0 pounds and 20 milliamperes at 100, or excuse me, at 75,000 pounds. All right. All right, so the load cell is going to output 0 milliamperes at 0 pounds and 20 milliamps at 75,000 pounds. All right, so my first point, x1 is equal to 0 milliamperes. Okay, and y1 is equal to 0 pounds. Oh, I'm sorry. Let's see. Let's do 4 milliamps because most sensors are going to output a 4 milliamp, like I say. So let's do the 4 milliamp example. Okay, and then x2 is fully loaded. We're going to be at 20 milliamperes, and y2 is 75,000 pounds. All right, so those are my ranges there. Let me just change the font just a hair so it'll all fit on one line. All right, so actually that was both points. Okay. So that was both points. So now we can say that the slope m is equal to y2 minus y1 divided by x2 minus x1. And so looking on the line above, that gives us 75,000 minus 0 divided by 20, and that's in pounds, right? That's in pounds. All right, and one thing I highly recommend that you do is keep units, keep the units, because you cannot subtract milliamps from pounds. And so if you write the units in here, you'll know that you're using the right numbers. And then we're going to have 20 milliamperes minus 4 milliamperes. Okay, so by writing in the units, you make sure that you're not making like a typo or a math calculation error. All right, because when you add and subtract your units must match. You can only add and subtract pounds to pounds and milliamperes to milliamperes. Okay, so this is going to then give us M. Okay, so this is going to be 75,000 pounds divided by 16 milliamperes. And so if I pull up my calculator here, I'll just pop into the Windows one at the moment. So we got 75,000 divided by 20 is equal to 3,750. Okay, so that's 3,750 pounds per milliamp. So what that means is that for every milliamp change I get out, I had a change in weight of 3,700 pounds. I like the blue, color blue, okay? Oops. So for every time you add 3,700 pounds, 3,750 pounds to this scale, to this load cell, you got to put on almost 4,000 pounds for the sensor to output an extra milliamp. Now, the sensor is perfectly allowed to output 0.2 milliamps or even 0.002 milliamps. Okay, so if you add on, and later on we'll talk about the resolution and we'll find out how many pounds you have to put on before we can tell that you changed something. And that's more on our analog to digital converter. So we'll discuss that in a different video. But for us to have one change in milliamps, we would actually have to output 3,700 pounds. We'd have to throw on 3,700 pounds to get the sensor to go from 0 milliamps to 1 full milliamp. So for the sensor to output the sensor is going to output 4 milliamps with nothing on it. So to get it to 5 milliamperes, we're going to have to throw on 3,750 pounds for the sensor to output 5 milliamps. And for the sensor, let me just kind of try and, well, I haven't found the slope yet. So let's do the slope, or not the intercept. I mean, that was the slope. I need to do the intercept. So the intercept, okay, the intercept B, lowercase b is with the symbol we use for the intercept, and the intercept B is defined as being y1 minus m times x1. Now I could also do this using y2 and x2. However, I like to use this because guess what? y1 is 0. All right, so it turns out then that B is going to be equal to y1, which is 0 pounds. So B is going to be 0 pounds minus M, which is 3,700 pounds, 3,750 pounds, divided by milliamps, times 4 milliamps, because remember, the sensor is going to output 4 milliamps when it's at 0 pounds. So at 0 pounds, I should be getting 4 milliamps. Okay, so the intercept then is 4 times 3750 pounds. So notice here, what's going to happen is, I'm looking for the strike through here. Okay, so where's regular? There it is, strike through. Okay, so see, the milliamps are going to cancel, because here you have X is in milliamps. Okay, this is X right here. X is in milliamps, and you're multiplying it times 3,750 pounds per milliamp. So the milliamps disappear, and you're left with pounds. All right, so it's very important that you watch your units so that you so that your scaling is correct. All right, and so now, so B, if I finish it here, then B is equal to, I got to multiply this out. So I have my 3750, multiply that times 4, and so I need to subtract off, I have to subtract off 15,000 pounds. Okay, so our intercept is minus, notice the negative sign here. Okay, this is negative. Font, underline. I don't know, I was trying to highlight there. Anyhow, but that is minus 15,000 pounds. So if I wanted to know, okay, what is the weight on the scale? Okay, so the weight on the scale is going to be M times X. Well, okay, X is what the sensor is reading. Okay, so X here, X is what the sensor is reading. Okay. X is what the sensor is actually reading. Okay, so call it sensor output if you want. So M is the slope times the sensor output. Okay, the sensor is outputting whatever the sensor is outputting in milliamps, okay, minus 15,000 pounds. So remember that M is the slope. M is actually in pounds per milliamp, right? So the milliamps are going to cancel. Okay. So then the milliamps are going to cancel, and then we have to subtract off an extra 15,000 pounds. All right, so let's say let's find out then if my sensor is outputting 4 milliamps. Okay, so if my sensor is outputting 4 milliamperes, then that means that I've got 0 pounds. If my sensor is outputting 8 milliamperes, okay, so if my sensor is outputting 8 milliamperes, I'm going to have the slope, okay? So my equation, right, this M was 3750. 3750 pounds. That was that slope. And so my sensor is going to be outputting. We have to scale this. So we take our 3750, if I can hit the right key, 3750 pounds per milliamp times 8 milliamps. Okay, so the milliamps are going to cancel. They're going to go away. Minus an extra 15,000 pounds. All right. And so 8 times 3750 is 30,000 pounds. Okay, so so this is going to be 30,000 pounds minus the 15,000 pounds minus the 30, right, which is going to leave me with 15,000 pounds. All right, so, and this is at 20, you know, this is basically at the 25% mark that we were talking about earlier. Okay, so I'm going to duplicate this slide again so I can wipe out this top stuff, but still have it if we want to flip back to it. Okay, so I'm just trying to get this all on this slide so you guys can see it. Okay, so that when our sensor is at 25%, okay, we're at 8 milliamperes, and so we're actually going to be outputting what the sensor is telling us, okay, is that we are at 15,000 pounds. Okay. If the sensor is at 50%, then it's going to be outputting 12 milliamperes, right, which is going to be 750 pounds per milliampere times the 12 milliampere minus the 15,000 pounds. And so I'm going to guess that this is probably 45,000, right? So 12 times 3750. Let's just do it to make sure. So 12 times 3750 is 45,000 minus the 15,000, which puts me at 30,000 pounds. Okay. And if the sensor is at the full 100%, that means the sensor is outputting 20 milliamperes. So we're going to have 3750 pounds per milliampere times the 20 milliamperes minus the 15,000 pounds. Okay, so 20 times 3750 is equal to 75,000. All right. 20 times 3750 is equal to 75,000. Minus 15,000 pounds gives me 60. I must have made a mistake here somewhere. That would say I'm at 60,000 pounds. Let me see. 75 minus 0 divided by 16. Okay, there's my mistake. I divided by 20. Yeah, thank you. You pointed it out. I need to look at the chat. I didn't hear the chat ding, or maybe I thought it was an dinging. I'm sorry. You pointed that out. Yes. Sorry about that. You caught me. But I did not look. I appreciate you paying attention there. So, yeah, when I did my division, okay, I had the equation right, but I didn't type in the right value in the calculator. And I should have looked at the chat window. Thanks. Okay, so so let's do it again here. Sorry about that. So the 75,000 minus 0, and then 20 minus 4. 20 minus 4 is 16. And I did write that, but I didn't punch it in the calculator. Okay, so 75,000 divided by 16 is equal to 46,875. So that's what I should have here. 46,785 pounds per milliamp. So this here should also be 47,6875. And this one should be that. And this one should be that. Okay. And so, all right. So, yeah. Now, one thing I want to actually point out, this is 5 significant digits. Okay. Notice there's a 4, a 6, 8, 7.5. That's 5 digits. You want to make sure that you use 5 digits when you're doing the scaling, because if you don't, you can get round off error. All right. So when I ask you to do scaling, I actually specify to give me 5 digits. All right. So and now I need to go back and calculate those. So we're getting this 15,000 pounds was not correct. I have to correct that. So it was 46,875 times 4. And it's 18,750 pounds. Okay. 18,750 pounds is, I guess I had a couple of extra zeros on that one anyhow. All right, so then 46,875 5 times 8 is 3,750. £3,750 minus the 18,750. Okay, which is 18,750, which is what I was actually expecting. All right, so then if we pop down to, let's see, All right, so if my sensor is reading 12 milliamperes, right, which was 50%, right? So, and this was 8 milliamperes is 25%. Okay, so at 50%, we should have 46,000 times the 12 milliamperes minus the 18,750. Okay, and so that gives us trying to copy it here, save me a little bit of typing. All right, so this is going to give us 12. So we've got 12 times 37, or shoot, using the old number, 87.5. I missed a zero. I need to look at the chat more. 37,500. Oh, I see. Okay, so I'm just missing the zero there, right? Is that better? 37. Yeah. Okay. Yeah, just on the top one, I need to finish this. Okay, times 12 equals 56,000. So this one is 56,000. 56,250. Okay, 56 times 250 minus the 1870. You guys agree with that? I'll look at chat this time, make sure. Okay, minus 18,750 is 37,500. Which, by the way, 50%, remember, let me pop back up here for a minute. Remember our original load cell, I said could do 75,000 pounds. And so at 50%, you should be at half of 75,000, right? So that's a quick check. All right. And so then at 100%, so if we go to 100%, that should be 20 milliamperes. So this would be 20. And before I find out what this value is here, right, this value should be 7,500. So let's just make sure that works out. Okay. So I'm going to take 4687.5 times 20 milliamperes, and that's 93,750, but I've got to subtract off the 18,000 here. Okay. So this is 93,750 minus the 18,750. And I better be at 75,000 pounds now. Okay. So, yeah, I appreciate you guys catching that. I wish I would have, I don't know. It's, yeah, the chat is not dinging. Normally the chat dings. I'm not sure if I got my sound turned off or something on here, or very low. No, sound's all the way up. Not quite sure why I'm not hearing it ding there, but all right. So this is the scaling. So let me put the equation back here. I mean, I kind of have it here. So remember, we have our equation that the weight of this on this scale or on this load cell is equal to 4,687.5 pounds per milliampere, and we're going to multiply that times our number of milliamps. We're going to multiply that times the number of milliamps. And then what we're going to do is we're going to subtract off 18,750 pounds. Okay, so this is our equation. This is the equation of this line, right? Here's the equation of this line, the slope-intercept form. We have the slope m times x plus b. Well, our plus b, when you're doing 4 to 20 milliamps, and you're going in this direction, you're almost always going to have a negative b. Well, if you're doing if you have a 4 to 20 milliamp kind of sensor output, and you want to convert that back into the actual process variable, you're always going to have a negative b, okay? Because you got to subtract that back off because at 0, you're at a positive 4 milliamps. Right? At 0, you're at a positive 4 milliamps, so you're going to have to subtract off. So that's why if you're going from milliamps back into your process variable, you're going to have to subtract that off. And that's what we're doing here. So the weight on our scale is this slope. This is our slope, 4,687.5 pounds per milliamp, times however many milliamps that we have, and then subtract off, because the milliamps cancel out, you're left with pounds, and then you're going to subtract off the fact that at 0, you actually have 4 milliamps. You need to subtract that back off. So this is our equation that we need. So for those of you who got your chat working here, right? How do you do how do you evaluate an equation in ladder logic? How do that? Do you know how to do that? I mean, you should. You've been through plc1, right? So you should know how to do a mathematical equation. Anybody know what that's called? I'll let you guys put it in the chat there for a minute here. So did everybody lose their keyboard or can't think of what it is? Okay. Well, what you need to do is a compute statement. Okay. I've got it down here in the slides somewhere. These are the scaling slides I'm looking at. But what we need is a compute statement. Okay. So CPT is a compute statement. And so what we're going to do is we're going to have our slope and our intercept is all in this. And the destination, okay, the destination is your y side, your left side. So where was I here? All right, so here it is. All right, so this is the y side, right? That's your destination tag. All right, so what I'm going to do is I'm going to actually just program this in here. So I'm going to pop over to my RS Logix 5000, okay? And remember that this guy is in engineering units. Now, the only problem that we have, I guess before I program this in here, I have one problem. This was done in milliamps. But technically, inside my PLC, it's not giving me milliamps. It's giving me microamps. All right, and so to get milliamps, I'm going to have to divide. Okay, so let me raise this up a little bit here. All right, so to get milliamps, is equal to 1,000 microamps. So what they're giving me is microamps. All right, so the input that they're giving us is in microamps. So I'm going to have to divide this by an extra 1,000 microamps, okay, to make it milliamps. All right, so that's going to be my equation. So I'm going to come over here. I'm going to go offline. I'm going to go to my ladder logic. Or actually, no, I'm going to go to my tags. I created a couple of tags here, but it's not the example I'm doing. So I'm going to create a new tag. Hello, there it goes. Edit tags. I'm going to create a new tag. My new tag is going to be the weight on the load cell. Okay, and it's just going to be a number we're going to compute inside there. So there's no alias. Remember, aliases are things that are being physically wired out or in if it's an input. So it's a physical input or output wiring. All right, so I don't have an alias, but I need a real value here. So I'm going to come over here and say real. Okay, so notice here I just had to type RE and hit enter. Okay, if you want to do it the slow way, you can click on the pretty little dots and you can scroll up and down through this list until you find R's and find real and select it. All right, but if you know you want real, just RE, enter, you're done. Okay, that's for another line here, but okay. Now, if you end up getting a line you want to get rid of, click over here to the far left of the thing and hit delete. Hit the delete key and it'll disappear. All right, so here's my destination, weight on the load cell. So I'm going to come over here to my ladder logic now, and I'm going to add a rung. So I'm going to click over here on the rung somewhere, and I'm going to add a rung, or I could just do a Control R. They tell you the shortcut keys there. All right, and I'm going to add a rung, and I'm going to do this for all time. So I'm going to have nothing on the left side, but I'm going to come over to my compute and grab a CPT, and the destination is going to be my weight on the load cell. And my equation now, I done forgot my equation. I got to look back over here at my PowerPoint. All right, so my equation right there at the bottom, or my expression, as they call it expression, but that's going to be 4687.5 times, okay, so I forgot what my tag name was. So I flip back over here and look at my tag name. So my tag name is channel 1 is in engineering units, which is in microamps. So remember, right, these engineering units are technically microamps. Okay, so you can even name it that way you want. You call it channel 1, which is going to be in microamps. Microamperes technically, right? And so you can name it that, microamperes. When you name it something like that, that's what we call self-documentation. It helps you keep track of what this is. So this is in microamperes, and then I'm going to subtract off minus 18,750, which is in pounds. Okay, so this weight on the load cell will be in pounds. All right, and so if I download this and run this now, my number is out of town. Look at that number. What's going on there? Does anybody know? I got a load cell that can handle 75,000 pounds, and I got 8 million pounds on it. Okay. Go offline. I forgot. I said to do it, but I did not do it. Okay. I forgot to divide this microamperes by 1,000 microamps, right? So I forgot to divide it into milliamperes, because my calculation was originally done in milliamperes, but the problem is that microamperes, not micro Siemens, but yes, correct. Thank you. So we needed to divide. I was saying it, but I forgot to actually type it in there. So, whoops. So I just want to download this one more time, and now my number should be good. All right, so now if we look, you can see the value changing there, but I want to flip over to the tags. I think it's just a little bit easier to see. So let me see if I can fit these both on the screen here. All right, so when my thing is 50%, okay, so when it's at when it's at 0, right, my weight should be at 0. When it's at 2500, my weight should be at 18750. Okay, when it's at 37.5, where's it at? There's it's at 2500. I should have deleted those other ones there. All right, so when it's at 50%, it should be at 3700. And when it's at 100%, it should be at 75,000 pounds. But remember that because I've got these things daisy chained, I have too many of them daisy chained. And this particular thing can't handle that much output. So it's not quite getting, even though it says up the top, that's what I'm outputting, the card is being overloaded. So I really need to change my wiring on this card and not overload it. So I imagine I could drive two outputs, but you can't, on this particular one, cannot drive 3 outputs. Okay, some cards I know you can drive 3 outputs, but this particular one I can't drive 3 outputs, and I'm trying to. So when it tries to hit that maximum of 20 milliamps, it's just not making it. Right, but you can see that when it's at 0, we're at minus 500, which is basically 0, right? We're talking about thousands of pounds, so 500 is kind of small. And when we're at 25%, okay, so right there we're at 25%, we're at 18,000 pounds. And then when we're at 50%, we're at 37,000 pounds. Okay, so if I would not have overloaded my output card by trying to drive 3 inputs, it would actually be hitting 75,000 pounds right now when it's at 100%. Okay, so is there any questions? I know some of you were putting in the chat, so you seem like you were following okay, which I'm glad of. Sorry about that math mistake. I wish I would have glanced over at the chat window earlier. I would have caught it. Or, well, you guys caught it, and I would have been able to correct it sooner. But, yeah, so I just punched the number in incorrectly there. So fortunately, everything I was doing was correct, except for when I punched it in the calculator. Well, like I say, when you come in, what we're doing here is evaluating our equation, right? Here is our equation. On the left side, we have the weight on the scale or on the load cell. So I actually named that over here weight on load cell. So I spelled it like this: weight on load cell. So this here piece was my destination, right? So in the ladder logic, that's my destination. So the side on the left side is your destination, and everything on the right side is the mathematical expression. The only thing is you can't actually type in units, right? Now I didn't, but this is the tag name, and in the tag name I was actually able to put the units there. Okay, But the other thing that we have to remember is with the Compact Logix, they're giving us microamperes. We have to make sure that we divide by 1,000 to get it into milliamperes in there. So, all right, but so, you know, hopefully this kind of gave you an introduction. Well, we're not done. I've got some other videos on scaling, all right, because we're going to be, scaling is a critical piece to setting up these analog sensors, because we don't really care how many milliamps the sensor is putting out. What we care of is what that number of milliamps is actually telling us. So are we, you know, do we have 37,000 pounds on this? We have 18,000 pounds or something in between, right? Because the sensor could put out, you know, 4.317 milliamperes. Well, actually, not 3. It should never be below 4 milliamperes, but it could put 4.012 milliamps, and that would tell you you've got, you know, a small weight on there. So what is that weight? How many pounds is that weight? And it will tell us that. Okay. So because this number here that we're seeing right there, that is in pounds. Okay. That is actually in pounds, and that's what we want to know because we're trying to measure pounds. Okay. On the other hand, maybe you want to know tons. Okay, so if we wanted to, we could come in here one more time, go offline. I'm going to take this, and I'm going to come back here to edit tags. This is the weight on the load cell in pounds. So again, we can kind of spell that out there. By the way, in this software, what you really need to do, you know, if you can't read everything, you need to just come up here to this little divider and drag it out a little wider so you can read it. It seems like a lot of times they don't give you much room. And so I highly recommend that, you know, if you're not seeing everything, just widen it so you can read it. So a lot of times, like the alias, they cut off the alias, which drives me nuts. So the first thing I got to do is come over here and slide this over so I can see entire alias. Okay, I think that's very important. The base tag I'm not too worried about because that's just repeating the alias. Okay, but anyhow, so now I'm going to do the weight in tons. Okay, and so this is going to be a real value also. And what I'm going to do here is I'm going to come over here and I'm going to copy my compute statement. But, okay, so the destination is going to be the weight in tons. And then the equation then, whoops, deleted the whole thing. I just meant to delete the expression. So my expression is simply going to be the weight on the load cell in pounds divided by 2,000 to make it tons. Okay. And let's see, and I'm going to delete, I created these other ones because I thought that maybe I would do those, but I'm not going to do them now. I don't think we really have too much more time. So I'm going to delete them so they're not in the mix there. And I'll download this. All right, so now, you know, at 0, we should be basically at 0 tons or 0 pounds, okay? And at 50%, right, we're at 18 tons. And at, let's see, 0, right, we're basically 0 tons. At a quarter goes by so fast, I keep missing it. Okay, so at a quarter ton, Okay, at a quarter or a quarter percent, we're at 9 tons. Okay, all right, because basically 75,000 pounds is 36 tons. Okay. So we can, these compute statements now can give us it in any weight that we want. All right, so that's about all I'm going to do for this evening. Is there any questions on this bit? All right, so remember that there is going to be class, barring any kind of crazy, weather storm or anything. Hopefully next week, we will meet Tuesday. We're going to do, the first lab is the just the analog signal lab, and we're going to build a circuit that's going to give us 4 to 20 milliamps, and we're just going to hook up a digital multimeter to it and measure that circuit. And if you guys want, if you have time, it's really not part of the lab, but if you want, we can do some very basic ladder logic and feed it into the PLC if we have time. So, we could do something like that pretty quickly, but that's not officially in the